Everything we graphed in this class so far has either been a straight line or an absolute value. So we're going to draw on both of those today. We're going to be looking at quadratic functions. So a quadratic function is a function where we have not just x, but we have some x squared. So we have something where x is to the raised to the second power. That's a quadratic. So this is going to give us a different shape than what we've looked at. So anything that we graph, any equation that has just x in it, x and some other numbers, that's going to be a linear equation. That's going to give you a straight line when you graph it. But things that have x squared in them, this is not going to give us a straight line. It's going to give us some shape called a parabola. So the parabolas have a parent function. The parent function is just y equals x squared, or f of x equals x squared. So anytime you don't know how to graph something, you can just make a table, plug in some random x values, and see what happens. So I get students all the time coming to me saying, hey, Mr. Sherry, I don't know how to graph this. I don't know what this graph looks like. Well, anytime you don't know what it looks like, just plug in some random x values. The graph will take shape as you find the y values, and you can kind of learn what it looks like just by plugging in some random values. So you should never be stuck without knowing how to graph something, because you can always just throw numbers into it and just see what happens. So let's do just that. Numbers I'm going to throw into it are -3 going all the way up to 3. So the function here is x squared. All right, let's find f of -3. So that means we're going to plug -3 in for x. So we get -3 squared. Well, remember what it means to square something. That means to multiply it by itself. So -3 times -3, that's +9. If we square -2, again, that's -2 times -2, that's going to be +4. -1 times -1 is +1. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. Let's plot these points. Now you'll notice this does not give you a straight line. It gives you something that has curvature to it. So let's try to approximate this curvature best we can. And we get something that looks like that. So that is a parabola. And that is the parent function for all quadratics. Now let's graph something that has something other than x squared in it. So let's graph 2x squared. So again, we could just throw numbers into that equation and just see what happens. But let's think about actually what's going on here. So if we have 2 times x squared, well, that's just 2 times what we just did. So if we take all the y values that we just found and double them all, that will give us the graph of 2x squared. So if we say, look at the fact that here at x equals 2, we went up to 4 last time. Well, let's double that, go up to 8. Or we could do this on the points here. So at x equals 2, we got 4. Well, double that, we get 8. We could go through and double all these y values. So this would be 18, this would be 8, this would be 2, 0, 2, and 18. Well, we can't plot those 18s because the graph doesn't go up that far, and I'm not going to worry about extending it, but we can double all of these x values, all of the y values here that are still on the graph. And then if we approximate that curvature, we get something like that. And so you can see the graph of 2x squared is very similar to x squared, but it's a little bit taller and thinner. So since we've multiplied all the y values by 2 there, we've kind of stretched the graph upwards. So that's what the 2 does. I've drawn on here, for example, to the parent function, just so that we can compare what we do to the parent function. So the parent function's in red. I'm going to do the regular graph in green. All right, so f of x equals -1/2 x squared plus 3. Again, if you don't know what a graph is going to look like, just plug in some random values, see what happens. So let's make a table, and I'll plug in all the same values, -3, -2, -1, 0, 1, 2, and 3. So let's see what happens if we plug in -3. So this is f of -3. That's 1/2 times -3 squared plus 3. Following the order of operations here, we need to do the squaring first. So let's do -3 squared, which is 9, and then multiply by 1/2. 9 times -1/2 is -4.5. add 3 to that, and we get negative 1.5. So f of negative 3, that's the y value when x is negative 3, is negative 1.5. So then you want to go through and do that for all the rest of those x values. And that's what you should get when you put them all into the equation for x. Now there's one of these I want to point out, and that is the y-intercept, 0, 3. So remember that if you're looking for the y-intercept where the graph crosses the y-axis, that's the vertical axis, to get that, what you need to do is plug in 0 for x. So again, 0 tells you left to right. So if you're right in the middle, you're going to plug in 0 for x. You plug that in, and then you get negative 1/2 times 0 squared plus 3. Well, 0 squared is 0, times negative 1/2 is 0. This all goes away, and you're just left with that number at the end there. So just like with the absolute values, that's going to raise the graph up 3. So think about that as being a translation up 3, moving that y-intercept up 3. All right, so let's plot these points then. So the point 0, 3 that we were just talking about. 1, 2.5, that's right here. 2, 1, and 3, negative 1.5. That's right here. All right, and then plot the others. Now you might notice here that parabolas are symmetric. So the left side is the same thing as the right side, just the mirror image. All right, and let's graph this curvature here. Something like that. Now let's compare this to the parent function. So the obvious one here is that it's flipped the other way. So it's opening downwards instead of upwards. So that's the major difference. And just like with absolute value transformations, that's because the number we're multiplying by out front is negative. That will flip over the absolute value. It'll also flip over the parabola. Now, also like absolute value, but a little bit different, that 1/2 in front, that's going to change kind of how stretched or squashed the graph is. So with the absolute value, it would change kind of how the v opens. It would change the slope of the line for the v. Well, with the parabola, we don't have a line, so the slope kind of loses meaning here because we have a curved line, and so the slope at every point along this graph is different than at every other point. So there's no 2 points on this graph where the slope is the same. And so we can't really talk about it changing the slope, but we can talk about it changing kind of the general shape of the graph, whether it's tall and skinny or short and fat. And so that 1/2 kind of shrinks the graph down a little bit, makes it a little bit shorter and fatter. And then the +3, just like we talked about, will raise the graph up 3. So the vertex goes from being at 0, 0 to being at 0, 3. The vertex, by the way, is that cusp, is that turning point in the graph. All right, let's circle all the x and y intercepts. Start with x-intercepts. Well, the x-intercepts are right here and right here for the green graph. And for the red graph, it's the vertex right here at 0, 0. Now let's circle y-intercepts. So the y-intercepts for the green one, well, there's really just one y-intercept actually, and it's the vertex. Now it won't always be the vertex, the y-intercept. It just happens to be for both of these graphs that the y-intercept is the vertex. And then the vertex for each of these, well, we've actually already circled the vertex as it happens, but the vertex is these 2 points right here. So that extreme value, which is the either minimum or maximum value for the parabola. So if you think back to lines, the question at the bottom there, why didn't we discuss minimums and maximums when we were dealing with lines? Well, a line, looking something like that, will extend upwards forever, and it will extend downwards forever. So there's no such thing as a minimum or maximum value. But if you look at, say, that green graph, well, this point right here, the vertex, that is the highest that graph will ever get. There's no y value higher than that point. So that is the absolute maximum for that graph. Similarly with the red graph, this vertex here, there is no point on that red graph that is lower than that point right there. It is the lowest point, the absolute lowest point. So it is the minimum value for that parabola. Now a couple more questions here. Can a parabola have both a minimum and a maximum? Well, again, if you think about how they look, they either open down or they open up. So that's going to give them either a maximum or a minimum. You can't have both. You can't have neither. You're always going to have one or the other depending on which way it opens up. Okay, example 3. Again, if you don't know how to graph something, just plug in some random values. So let's do just that. All right, let's choose, say, -3, -2, -1, 0, 1, 2, and 3. We'll plug all those in and see what we get. So let's start with, say, -3. So y is equal to 2 times -3 squared minus 8 times -3 plus 6. And let's work this out. So make sure that you follow the order of operations. -3 squared is -3 times -3. We got to do that exponent first. That's going to give us 9. 2 times 9 then is 18. 8 times -3 is positive 24, then plus 6. So we get 18 plus 24 plus 6. 24 plus 6 is 30. 18 plus 30 is 48. So we get some real big number here. Okay, so maybe we got to try some different numbers. Maybe let's plug in 0. See what happens when we plug in 0. Okay, so 2 times 0 squared minus 8 times 0 plus 6. Well, 2 times 0 squared, that's just 0. That'll go away, and look, we get that number there. Okay, so that's a nice point on the graph. All right, so maybe 1 and -1 we could plug in. So the point here is that just plugging in random numbers may not always give you numbers that are kind of practical to use. So that when we plugged in -3 here, just like we had been doing for the other graphs, we got 48, some big number. Well, we don't want to use that. So you may have to poke around a little bit and plug in some numbers that are farther away from each other and just kind of experiment with it, see what numbers will come out that can kind of lay nicely on the graph. So if you poke around with that a bit more, you might be able to find some good numbers to use. So I just went through and plugged in a whole bunch more numbers into this graph, and we get that table there. So let's plot some of these points, at least the ones that we can plot. So there's the point 0, 6, which is the y-intercept, where x is 0. There's the point 1, 0, which is an x-intercept, because y is 0. 2, -2. 3, 3. Hold on, that might be wrong. Yeah, that should be 3, 0, not 3, 3. My apologies. 3, 0, and then 4, 6. That's right here. And then the rest are off the graph. So you can see here our parabola has been shifted around. So unlike the parent function, again, the parent function looks like this. So it's been shifted to the right and down from the parent function. Now, since it's been shifted to the right and down, there's a couple things that happen. One, you'll notice that there are now 2 x-intercepts instead of 1. And also the y-intercept is not the vertex. All right, so let's look at the vertex, the line that goes through the vertex. So this line is a very important line. We're talking about the vertical line, I should specify, that goes through the vertex. That's, in this case, the line x equals 2. That is called the line of reflection. And this is a very important line because if you notice, every point on one side of this line is reflected onto the other side of the line. It's also called the axis of symmetry because the parabola is symmetric over this line. So, you think about these 2 points here. Well, there's a distance of 1 to the line, and then if we go 1 more, we get back onto the parabola. Here there's a distance of 2 between that point and the line. If we go another 2, we get back onto the parabola. So it is symmetric. And any point here, this point reflected over the line, we get this point. Every point is the reflection of every other point over this line x equals 2. Now, that line is the line x equals negative b over 2a. So remember the standard form ax squared plus bx plus c. So the number in front of x squared is a, the number in front of x is b, the number without an x is c. So if we look at negative b over 2a, well, for this, this equation right here, b is negative 8. So if we have negative b, that's going to be negative 8 over 2 times a, so that's 2 times 2 in this case. So we have two negatives here, negative and a negative is positive, so that's going to be positive 8 over 4. 8 divided by 4 is 2. So you can see x equals 2, that is the line that we drew. So this is a very important thing because it allows you to not have to just take a shot in the dark as to what points you're plugging in. So if you remember the first point we plugged in was negative 348, well that's that's kind of a pain in the butt to have to be just plugging in random numbers to try to see where the graph is. So if you know where that axis of symmetry is, if you know where the x value of the vertex is, then that can help you find the rest of the graph much more quickly. So remember negative b over 2a, that can help you find the x value of the vertex, which is the axis of symmetry as well. All right, so now we've of course already graphed this, and so we know what the y value of the vertex is. But if we were graphing this from scratch, and say we found negative b over 2a first, and use that to find the other points, well, if we wanted to find the y value of the vertex, well, we could take this x equals 2, plug it back into the equation for x, and then find the y value algebraically. So let's just do that real quick as an exercise. So we do y equals 2 times 2 squared, then minus 8 times 2 plus 6. Well, if we square 2, that's going to be 4. And remember, we got to do exponents first, so this has got to happen first. That's 4 times 2. Then 8 times 2 is 16 plus 6. Well, 2 times 4 is, that's 8 minus 16 is negative 8 plus 6. We get negative 2. And that's this coordinate point that we found right here. That's the vertex to negative 2. All right, so this at the bottom here, this is the formula that you're going to use. Now that looks a bit scary, but all that really is a coordinate point x and y. The x value is this negative b over 2a that we got from this line. And then for the y value where it says f of negative b over 2a, that just means take the x value that you find, plug it into the equation to find the y value, which is exactly what we did just above there. So you use negative b over 2a to find the x value of the vertex, just plug that into the function to get the y value. That's all that vertex formula means. And last, without graphing, find the vertex of this parabola. So we're going to do negative b over 2a to find the x coordinate. So that's negative 6 divided by 2 times 3 halves, which is negative 6 divided by 3, which is negative 2. So the x coordinate of the vertex is negative 2. We can plug that in then to find the y coordinate. So it's going to be 3 halves times negative 2 squared plus 6 times negative 2 plus 4. Negative 2 squared is 4. And that's going to be plus negative 12 plus 4. 3 halves times 4. Well, 4 divided by 2 is 2, so that's really 3 times 2, which is 6, minus 12 plus 4. 6 minus 12 is negative 6, plus 4, and then negative 6 plus 4 is negative 2. So the vertex of this parabola is negative 2, negative 2. So that's a really nice way to start graphing from standard form, is just finding the vertex by using negative b over 2a, plug that value in to get the y value of the vertex. And then to get the rest of the graph, you can just choose a few points to the left of the vertex, choose a few points to the right of the vertex, and then graph those points. All right, next question. Is this vertex a minimum or maximum? So in order to do this, we need to know whether the parabola opens up or down. So we could just graph it and see, but let's think about it instead. So this number out front, that determines whether it opens up or down. This is a positive number, and so that means it's going to open upwards. So that means there's a value at the bottom that is the lowest value on the entire graph, which is this point, negative 2, 2. So the vertex here is going to be a minimum. As far as the y-intercept goes, well, that's going to be when we plug in 0 for x. So if we were to plug in 0 for x into this equation, well, this thing would go away because that's 0. This thing would go away because that's 0. And this last number is going to be the y-intercept. And so we know that has to be the y-intercept because that's what we get when we plug in 0 for x.